Hello everybody, welcome to today's Lead Code problem solving session. Today's problem is 633 sum of square numbers. Given a non-integer array C, given a non-negative integer C, decide whether there's two integers A and B such that A square plus B square is equal to C. Basically, we are given an integer and we have to find out whether it's a sum of two squares. Um, I had some time to think of like the solution before I started recording. So I have a solid solution that will work. So basically, the solution that I'm going to use is there are like multiple approaches, I guess, for this problem. And the one I'm going to use is that uh, I'll start with the basic approach and then I'll go ahead and come up with a better approach. So basically, we are looking for uh, an A which is less than root of c, because if a, oh wait, yeah, so if we kind of like reformulate this question, so basically we have a power 2 plus b power 2 is equal to c, and we're looking for an a which is uh, square root of c minus b squared, or like much better is a square. Which is equal to like, yeah, c minus b power 2. Let's start with I actually. Uh, let's use an I, and let's write a while loop instead of a for loop. So while I square less than, yeah, this should have said decide whether there's two positive integers, because I guess that could be like a number. Ah, no, my bad. Yeah, it could be like I guess 4, and 4 could be like 2 square plus 0 square. I guess that's also valid. So, well, I square less than 0, less than, sorry, C, less than, let's see, let's use less than equal to C. We say A is equal to I square and B is equal to A. Yeah, let's call this b squared, okay? C minus a. Guess we can start with a because like let's call this a so we don't have any confusion. And if square root of b square is same as the integer version of square root of b square, return true. And we increase a plus a by 1. And this should work because we have c, which is a huge number, but which goes at a like 10 power of 9, I guess, but then or like 10 power 10. But square root of that would like be not so large, like at least like half the power of like 10 power, you know. Wrong answer. Interesting, interesting. So output is 4, but expected is 2 because because 4 plus 4 is a valid number. No, print A. I'm surprised that we didn't get to A, which is like as close to what we're looking for. Oh, square, square. Oh, wow, 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 wow. Wait, what? I'm not even sure how that even worked in the first place, but just what it is. Lead code being lead code, I guess. So yeah, it did work. Mm, now there's like, I believe there's like a other way we can do with binary search, is it? It's not here, but looked into the solutions before, uh, and there's like a thinking about this problem. It's like a binary search that we can do. See, based on the intuition I gain, we can like do it here. No, I think it doesn't make sense. Yeah, let me just like look into the solution I was looking at before and come back. Okay, I went back and looked into the solutions to find a better solution. So the binary search solution that I was looking for, that I had in my mind, that's not really good in terms of efficiency or whatever because, um, yeah, it, the square root of b is being calculated using binary search. So, sure, like the inbuilt square root function is probably better. So I'm going to like basically use this uh, writing from the solution to come up with a better solution, which is basically it's called uh, it's called something. Yeah, and it's called Fermat's theorem. Let's just put it here. Yeah. So basically, the idea is that any positive number n is expressible as a sum of two squares if and only if the prime factorization of n, every prime of the form 4k plus 3 occurs at an even number of times. So we start with I is equal to 2 plus while I is equal to 2 and while I less than square root of n or of c, we increase I plus 1 at the end. First we basically look uh, it's the count of primes. So basically uh, we start with like a count 0, and while c mod I is 0 for that time factor. So basically, yeah, we increase the count and divide c by that prime factor. So the idea is that once we divide something by its prime factor, we don't need that value again. And like once we remove that particular prime factor, like we divide uh, any number of times, it's just gonna go away from here. Mm, yeah, since like 0, let's do this here. And if I mod 4 is 3, so we're checking if it's in the form of k plus 3, right? And count the number of times that I has appeared. Mod 2 is not equal to 0, we return false. basically what we check at the end is that we check for this in the case where C is a prime number, it won't be divisible by any of the primes in the like this range 2 to square root of C. So if C mod 4, so he's basically return, yeah, I mean, we can just return C mod 3. Let's do this. Yeah, I think this should run fine. Yeah, syntax error, body syntax error. Now I'm using curly brackets in Python 3. This is what happens when you like when I've been coding in like one language for a long time and then like I try to mix it up because I want to like know more than Python, obviously. Actually, I think it's working. It should be better than, significantly better than the previous solution. Oh, it's actually way better. But sure, let's analyze the complexity. Let's see. I mean, I don't know the complexity of this problem. But yeah, it should be close to the one that is given because we're basically computing all the prime factors, which kind of gives us the root anyway. I think it's basically counting on this, which I guess is fair. I don't know. But yeah, thank you for watching. Peace.